So in this particular velocity versus time graph video, we have the motion of a runner plotted for the first 14 seconds. So as you can see in this graph here, the runner is starting from rest, aka the initial velocity is 0. It starts at the origin. And then as you can see, the velocity increases to a velocity of 10 meters per second towards the right. And then here, it just keeps it constant at a rate of 10 meters per second, aka the acceleration is 0. And then from 10 meters per second, the runner slowly accelerates down to 0 meters per second. And then once the runner stops, the runner now actually moves in a negative direction. I know this because all these values from 10 to 14 is below the t-axis, aka the time axis. And all these values here are negative. Negative velocity would suggest that the object is moving leftward. Okay, so that's the gist of this particular velocity time graph. So again, it accelerates to a velocity of 10 meters per second. It keeps a constant rate, a constant velocity of 10 meters per second, slows down to 0. And then from 0, the runner changes direction and moves in the opposite direction, aka in this case is negative, leftward. All right, so if you need to, read part A, B, C, D, E, F, and G, and then follow along. Okay. All right, so let's do part A, B, and C on this slide. So here's the graph again. So part A asks us to find the average acceleration during the first 4 seconds. So as you do these problems, always pay attention to the interval given to you. The time interval is super duper important, okay? Here, it says the first 4 seconds, so I know I want to start at 0 and end at 4 seconds. So I'm going to trace out my little graph real quick, okay? So here, from 0 to 4, and then from 4, I need to go all the way up to where the graph is, which is 10, okay? So here, average acceleration is broken into VF minus VI, change in time. Well, what's my VF? My final velocity at 4 seconds is 10 based on the graph. So I'm going to plug in VF as 10. Well, what's my initial velocity? My initial velocity on the graph at time equal to 0, it is 0 meters per second because this velocity time graph starts at the origin. So 10 minus 0 is 10. 10 divided by 4 is 2.5. Here, I include the plus sign because acceleration is a vector. So I do need to include the direction. So plus 2.5 meters per second squared. All right, so that's it for part A. Part B asks us to find the runner's average velocity during the first 8 seconds. Well, the first 8 seconds is from 0 to 8. Okay, so again, as you do these problems, pay attention to the wording. First 8 seconds imply from 0 seconds to 8 seconds. Well, to find the average velocity, all you have to do is use displacement over time. I do like to take this opportunity to point out the definition of average velocity is always this particular function, displacement over time. This works all the time, okay? This works all the time, and I'll tell you what other functions doesn't work sometimes. So if I have to choose to find average velocity, I will always rely on this particular function, which is the total displacement over the total time. Well, how do you find displacement? We know the time is 8 seconds, but how do you find delta x? So what's important to understand is that for a velocity versus time graph, the area underneath the graph itself is your delta x, your displacement. So this area that I have highlighted here in yellow, that is how far the object has gone, okay, in the first 4 seconds. So if I find this area, it actually tells me my displacement. And my displacement is going to be here positive because the area is above the time axis. So here's my t-axis that I'm tracing out with the cursor, okay. So any area that's above the time axis is a positive displacement. What does that mean? It just means the object is moving rightward. And that's all that you know. Whether it's speeding up or slowing down, you have to look at the graph. But you know that it's still moving to the right because the area is positive. So to find the first area here of this right triangle, we simply do 1/2 times base times height. The base is 4. Why? Because the time here starts at 0 and it goes to 4. Well, what's the height? The height is 10 because it's going to go from 0 meters per second to 10 meters per second. So the area is simply 1/2 times base times height. 4 times 10 is 40. 40 times 1/2 is 20. 20 what? 20 meters. And it's positive 20 meters because the area is above the t-axis, okay? But part B wants us to go the first 8 seconds. So I'm not done yet. I need to go from 4 to 8 now, okay? So that first part is the right triangle. The second segment here is just a rectangle. So this area here is super easy to find. The area of a rectangle is simply base times height. So let's knock it out real quick. Area here is base times height. Well, what's the base? From 4 to 8 is the difference of 4, aka the base is 4. The height is still 10 because if you go to the left side here where the velocity interval is, that's 10. So 4 times 10 is 40. 40 what? 40 meters to the right, or positive 40 meters. It's positive because both these areas are above the t-axis. So this is an important concept for you to understand as you practice velocity versus time graph, okay? The area beneath a velocity versus time graph is your displacement, which is a vector. All right, so therefore, if you're keeping up, my delta x here is 60. Why 60? Because 20 plus 40 is 60. Positive 20 plus positive 40 is positive 60, divided by 8 seconds. The 8 comes from the question itself. Part B says the first 8 seconds, so my change in time is 8. So if you plug in 60 meters divided by 8 seconds, you should get a value of 7.5 meters per second. Here I've chosen to put the plus sign because it asks for average velocity, and average velocity is a vector, so I do need to tell whoever's doing the problem that it is moving in the positive x direction, or eastward. Okay. Now, if you don't understand the concept of area, then you can do it mathematically using your kinematics equation. But you have to understand that this is two different acceleration. From 0 to 4, it is accelerating at some rate because that slope is a positive slope. But from 4 to 8, it is not accelerating because the slope here is 0. So right away, you have a positive slope and then you have 0 slope, so which is two different values, okay? Which means you have to use your kinematics equation separately. You cannot mesh things together. So I'm gonna show you how to do this. First, you need to learn how to chunk up these types of graphs, okay? Well, how do you know what to chunk? Well, based on the segments that's visually given to you. I want to chunk the first part from 0 to 4 seconds because that is a positive slope. Well, from 4 to 0 second, I can just use the information there and find my delta x using my kinematics equation. Delta x is vit plus 1/2 at squared. But if I start at 0, the graph tells me if I start at 0, my velocity is 0 because it starts at the origin. So I can just cross out vit. The only thing left then is just 1/2 at squared. So therefore I carry down the 1/2. Acceleration I just found over here, which is where my cursor is tracing. Right, there is a positive slope, and that slope happens to be 2.5. So therefore, I plug in a is 2.5. T here is 4 because the time interval here from 0 to 4. I want to square that. So if you punch all this in your calculator, you should get a value of 20, which is consistent with what we found over here. Earlier, when I shaded this area of the right triangle, I found that area by doing 1/2 times base times height, and the answer is 20. Well, it matches with my math response. Okay, let's do from 4 to 8. From 4 to 8, the quickest way I would do this problem is just find the area. Now, just in case you want to do it using physics function, you can, again, use your displacement function. You can go vit plus 1/2 at squared. But if the problem starts from 4 to 8 seconds, from 4 seconds here, the object is already moving. At 4 seconds, if you trace across here, the initial velocity is now 10, and then the time interval is 4. However, what I do notice is that the acceleration here is 0 because the slope here is flat. For a velocity versus time graph, the slope is your acceleration, but there is no slope here because the slope is just a straight flat line, which means acceleration is 0. Because acceleration is 0, I can cross out this 1/2 at squared out, okay? So 1/2 times 0 times t squared is just 0. So I can plug in my vi. You notice here my vi is 10, not 0, because this problem starts at 4 seconds. At 4 seconds, the graph tells me that it's moving at a rate of 10 meters per second. Well, how come my change in time is 4, not 8? Well, my change in time here is 4 because I'm doing the second segment, which is from 4 to 8, which is a difference of 4 seconds. 4 times 10, or 10 times 4, is 40 meters, which is consistent with what my cursor is tracing here. So when I found the area from 4 to 8 seconds, I noticed that the area is already 40. Well, 40 what? 40 meters. The area beneath the velocity versus time graph is your displacement. Positive 20 meters, positive 40 meters, which means the object is moving to the right. Okay, so this is one way to validate if your area is right. Or just crank out the physics function if you prefer. I like the area. Okay, let's do part C. Okay. Oh, this one I want to point out. This came up. I totally forgot. Earlier I said that if I had to, I would use this average velocity function all the time because it always works. Average velocity is, by definition, displacement over time. This function that just came up on the screen here, I want to move it back and forth, so hopefully it catches your eyes here. This particular function to find average velocity only works if acceleration is constant. but from 0 to 8 seconds, watch my cursor, from 0 to 8 seconds, the acceleration is not constant. This right here from 0 to 4 is constant 2.5, but from 4 to 8 is a constant of 0. Well, 2.5 and 0 are not the same. So while they're both constant, they are not the same constant, which means you cannot use this function at all, okay? Sometimes kids wants to put in VF plus VI divided by 2 for 0 to 8. And I would tell you, you cannot do that because acceleration is not the same value for the whole entire time. And if acceleration is not exactly the same value the whole entire time, you cannot use this function, okay? So make sure you use this function properly. Like for example, you can use this from 0 to 4, okay? Like you can use this function from 0 to 4. You can use it from 4 to 8, but you cannot use it from 0 to 8 because the acceleration from 0 to 4 is 2.5. The acceleration from 4 to 8 is 0, which is not the same. So you cannot use this. So keep in mind as you practice what is proper to do and what is not proper to do, okay? So that's super important. All right, part C wants us to find the instantaneous velocity at 2.3 seconds. Well, 2.3 seconds falls in between 0 and 4 seconds, so therefore it falls in between the shaded yellow area, which means I can use this kinematics equation. The final velocity is simply acceleration times time plus the initial, but it sits at 2.3 seconds, so I'm actually going to start my problem at 0 second and go to 2.3 seconds. Therefore, my acceleration is 2.5 meters per second square. That's what we found here, where my cursor is tracing back and forth. The acceleration for the first 4 seconds is 2.5 meters per second square. Well, my t is 2.3 seconds because I'm starting at 0 second and I'm ending at 2.3 seconds. But if I start at 0 second, my initial velocity here is 0 because the graph said so. So therefore, all you have to do is punch in 2.5 times 2.3 and your value is 5.75 meters per second. Again, here I've chosen to include the positive sign because it asks for instantaneous velocity, which is a vector, okay? So the answer is positive 5.75 meters per second, or you can say 5.75 meters per second east, whichever you prefer. All right, let's go part D. Part D is asked us to find the average acceleration during the 8 to 10 second. So again, if you look at this graph properly, there's the first segment, there's the second segment, there's the third segment, and there's the fourth segment. So this runner is running and behaving differently based on the time interval shown. So it's important for you to chunk out these types of graph. Well, average acceleration is change in velocity over change in time. Change in velocity is VF minus VI, but this particular problem wants us to find from 8 to 10 seconds. So 8 seconds now is my initial, 10 seconds now my final. So if you look at the graph properly, where my red lines are coming up, well, here is my rise over run, okay, rise over run. So at times equal to 8, my velocity is 10. That's what the graph shows me. So my initial is going to be 10. Well, what's my final velocity? At 10 seconds, the graph is at 0. So if you look at where that intersects, if you go all the way across, this velocity is 0. So final velocity is 0, initial is 10. So 0 minus 10 is negative 10, and then negative 10 divided by 2 seconds is negative 5 meters per second squared. Again, the 2 seconds is the difference between 8 to 10 seconds, okay? Which makes sense. If you look at the graph, this is a velocity time graph. The slope here is the negative value, which we got a negative value. And it went down 10 over 2. Well, 10 over 2 is a slope of 5. And it's negative because, well, from left to right, this is a negative slope, which makes sense. So that is your answer for part D. Let's do part E. Part E asks us to find what is the runner's instantaneous velocity, or excuse me, instantaneous speed. My bad. It says the absolute value here. Instantaneous speed. So essentially it says, look, find the velocity but leave out the direction at 9.2 seconds, okay? So 9.2 seconds falls between 8 and 10 seconds. And so this is how you kind of attack these problems. Look at the time given and see where it falls in between and just use the information for that particular segment. I'm just going to focus my attention between 8 to 10 because the time given is 9.2, which falls in between 8 and 10 seconds, okay? So just similar to the other part, our final velocity is our acceleration times time plus VI. Well, my acceleration for 8 to 10 seconds is negative 5, which we just found in part D. Well, how come my time is only 1.2 seconds? Because I'm starting at 8 seconds, and then from 8 to 9.2 seconds is a difference of 1.2 seconds, okay? So again, I keep saying this, it's important for you to understand where the problem starts and where it stops, and you have to use the information for that segment. Do not get things mixed up, okay? So the time here is 1.2. Well, what's my initial velocity? My initial velocity at 8 seconds is 10, okay? So don't put in 0 here just because time is equal to 0 is 0 meters per second. The problem starts at 8 seconds, so follow the graph, listen to the graph, listen to what it has to say. So velocity here is 10. So therefore my initial velocity for this interval from 8 to 10 is 10 meters per second. So if you plug this in your calculator, -5 times 1.2, which is -6. -6 plus 10 is +4 meters per second. And that is our answer. Here, once again, I caught myself earlier. It says instantaneous speed, aka the absolute value, and it says speed, so therefore it is a scalar, so I don't need any directions. So notice there, I put no directions. So the answer would simply be 4 meters per second. All right, let's do part F. Part F asks us to find the total distance for the entire 14 seconds. So for the whole entire graph shown. Well, distance is a scalar. So it's important that you keep this in mind, okay? Here, distance is a scalar. Distance is a scalar. So therefore, ignore all the signs. To find total distance, all you have to do is find all the areas. So I highlighted all the areas for you here. If you kept up with the previous part, if you need to rewind the video, the area of the first triangle here is 20. The area of the second rectangle here was 40. Now all I have to do is find this area. Well, this area for a right triangle is simply 1/2 times base times height. Well, what's my base? From 8 to 10 is my base. That's a difference of 2. That's why the 2's there. What's my height? Well, I want to go from 0 all the way up to 10 meters per second. So my height is 10. So 1/2 times 2 is 1. 1 times 10 is just 10. 10 meters in the right direction, because this area is still above the horizontal axis, which implies that it is a positive displacement. Now let's find this area. This blue area, as you can see, is beneath the t-axis, right? It's below the horizontal axis. Therefore, if we find this area, it is a right triangle, so we do 1/2 times base times height. The base is 4 because from 10 to 14 is 4. And then from where my cursor is, which is 0, go all the way down. That's a height of 5. So therefore 1/2 times 4 times 5 is 10. Now, distance is a scalar. So it doesn't matter whether the area is above or below. You simply add all the values and that is your answer. So therefore, I want to add 20 plus 40 plus 10 plus another 10. And that would be my distance, okay? So therefore, I have 20 plus 40 plus 10 plus 10. So therefore, the answer is just 80. So 20 plus 40, so 60. 60 plus 10, which is 70. And then 70 plus another 10, which is 80 meters. So distance is a scalar, so you just add all the areas. There is no such thing as negative distance. All right, let's do part G. Part G asks us to calculate the total displacement travel for the entire 14 seconds. Well, total displacement is a vector. Displacement is a vector, which is different than total distance. In the previous part F, we found total distance, which is a scalar. Here, I asked you to find total displacement for the whole entire graph. Keep in mind that displacement is a vector, so therefore, whether it's above the horizontal axis or below it is super, super important. Here, I make a note there. Displacement is a vector, so it's important that you differentiate between a scalar and a vector quantity. The first area, the second area, and the third area, which we already found in part F. Here, this area was 20, this area was 40, this area here, once again, is 10. It's positive 10 because it's above, and this blue area is below. So the difference here in my work is that here I include the negative sign. Well, why am I including the negative sign here? Because the area beneath, the horizontal axis, beneath the velocity versus time graph is my delta x, my displacement. Because it is a vector, below would imply negative, so therefore this area is negative. So to find the total displacement, I would simply add up all these areas, except now I have to include the direction. This area in yellow is above, so it's a positive 20. This area is above, so that's 40, positive 40. This area is above, so it's positive 10. This area is below, so this is negative 10. So I need to include the negative sign for vector stuff. So therefore, if we add all this up, 20 plus 40 is 60, plus 10 which is 70, but 10 plus negative 10, which is just 60. But here my answer would be positive 60 meters because I asked for displacement, which is a vector. Because vectors have direction, I need to let someone know that it is positive 60. So by the time the runner ran forward, the runner ran backward, the runner is still 60 meters to the right of his or her starting point. Okay, so that's that. Now, if you wanted to, you can use the kinematics equation to find the area of this kind of pink reddish area and blue. Okay, I already showed you how to do yellow and green earlier in the video. Now I can show you how to do red and blue. Well, to find the area for this particular from 8 to 10 seconds, again, it came out, the animation came off low, 8 to 10. If I start at 8 to 10, I can use my displacement function, which is vit plus 1/2 at squared. But here my vi is 10 because it starts at 8 seconds. So at 8 seconds, you know, if I go to the graph, I go all the way across, that's 10. So therefore my initial velocity is 10. My time is 2 because from 8 to 10 seconds, the difference is 2 seconds. The acceleration for this graph, if you need to rewind the video, this red area, the slope is negative 5 meters per second square. And then time here is 2 seconds, and I want to square that. So if you do all this correctly, 10 times 2 is 20. And then 1/2 times 5, you know, is, 1/2 times negative 5 is negative 2.5. And then negative 2.5 times 4, because 2 squares 4, which will give you negative 10. So 20 plus negative 10 is a positive 10, which is consistent with what we found here, okay? Again, in the blue, we already know that this is negative 10. Let's prove that it's negative 10. Well, I can use the same strategy, except I want to start at 10 seconds. I want to go to 14 seconds because the graph here says from 10 to 14. Well, if I start at 10 seconds and I go to 14 seconds, well, if I start at 10 seconds, the graph intersects at 0 here. So at 10 seconds, if I trace all the way to 0, okay, here it is. So therefore, I know my initial velocity is 0. I'm going to cross that out. Okay, I'm going to cross that out. VIT is crossed out because at 10 seconds, the object is at rest. And then here, 1/2 AT squared. If you find the slope of this particular from 10 to 14 seconds, it'll be a negative 1.25 because it's 5 down and 4 over. Okay, so 5 down and 4 over. So negative 5 divided by 4 is negative 1.25. And the time here is 4 seconds. I'm going to square that. And if I punch this in my calculator, I will get a negative value. I'll get a value of negative 10 meters. It's negative because, once again, the area is beneath the horizontal axis, which is consistent with what we found here. Okay, so you just have to differentiate between distance versus displacement. Distance, you add up all the areas because you cannot have negative distance. Displacement is a vector, so you can have negative displacement. Okay, so differentiate between distance and displacement. All right, other than that, I hope that helps. Good luck, stay nerdy, don't be whack.